Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at Ajay Kumar Garg Engineering College, Ghaziabad. I am before you to present the lecture for the complex topic for the subject Microwave and Radar Engineering, and whose code as per the AKGEC syllabus scheme, that is the KEC 074. So today I have selected the topic measurement of VSWR and the attenuation. So in this lecture, I would like to explain the how we can measure the VSWR and the attenuation from the microwave test bench. So in this lecture, the first topic, that is out of these two content, VSWR measurement. So in this VSWR measurement, so first one, what is this VSWR? This is nothing but simply a voltage standing wave ratio. Its full form is VSWR. Full form is the voltage standing wave ratio. That means when standing waves are created in a system, okay, when we will terminate with load, then the waves are reflected back, then one is incoming and someone is reflecting back, then the waves looks like the standing wave, where the waves have the maximum amplitude and the minimum amplitude of voltages. So the ratio of these two, ratio of voltage VSWR, if we say the ratio of V max to the V min. Okay, so this is the ratio of VSWR, is the ratio of V max to the V min, and its range lies from 1 to infinite. So for any system. But when we are calculating, so this is the simple formula, and if we have any values with us, then we can manually calculate the VSWR of any device. But when we are going for the microwave signal and from the microwave test bench, if we will see this, how we can measure. So for that point of view, what we are doing, we have just first calibrate the microwave test bench, which have include the have the number of sections, like first one it is klystron tube, then it is having the isolator, then it is having the attenuator, frequency meter, then slotted section, and the terminating load, or the meshed load. And from the slotted section we are giving to the output, taking either from the power meter, or we can say that with the help of CRO we can get the output. So this is the arrangement for the microwave test bench. So when we are initially calculating the VSWR, so it is classified in the two category as per the range of means as per the value. So it is, we are calculating in the two ways, like first one it is S less than greater S less than 10 range and S greater than 10. So for these two range we are calculating the microwave, we are calculating the measuring the value of VSWR. So in this first one we are considering the S less than 10, means measurement of low VSWR. Okay, so for that point of view, what we are doing, we are just simply connecting the microwave test bench, as which I have earlier sequence I have earlier told. So in this, the VSWR, measurement of low VSWR, can be done by adjusting the attenuator to get a reading on a DC voltmeter, which is simply a VSWR meter. So in this, what we are doing, so we are just calibrating the test bench, and after that calibration, what we are doing, after calibration we are simply connected, move the attenuator, okay, and after changing the adjusting the value of attenuator, we are getting the maximum value of voltage, and we are noting down. Okay, and after that we are calculating the adjusting the value like a way in this it will shows the maximum value. Minimum value of voltage we are calculating Vmax, and another time we are calculating adjusting the attenuator in such a way so it will give the minimum value V minimum. Okay, so in this way we are calculating these two values Vmax and Vmin, and after the getting this V value, maximum value of voltage and minimum values of voltage onto the DC voltmeter or VSWR meter, and we are taking the ratio of Vmax to Vmin, it will give the value of VSWR. Okay, so we can simply we can calculate the value of this VSWR. But when greater than 10 values, if we will go, so it is become congested to measure the values of the. So for that point of view, we are dealing with the another technique or another category, that is the measurement of high VSWR, that means S greater than 10. Okay, so in this, what actually we will do in this, the problem of congested setup will become congested in that way. So we are just moving toward the double minima method. Okay, so that means for greater than S greater than 10 value, we are considering the double minima method. So means it may here we are calculating the values of two minimum points we will calculate, and with the help of this we are calculating the value of VSWR. So in this actually what we are doing the measurement of high VSWR, that means S greater than high means S greater than 10, whose value is greater than 10 can be measured by a method called the double minima method, which is I have written here. So in this method, the reading at the minimum value is taken and the reading at the half point of minimum value in the crest before and crest after are also taken. So what we are doing in this, simply the setup what we have with us earlier for S less than 10, we will I have discussed with you. So in the same way, the setup will be the same, means our first one we are connecting the setup having the first one Klystron tube, then it will having isolator, then it will having the attenuator, then frequency meter, slotted section, and we are getting output from the slotted section at the CRO, and also we have the detector mount there at the end. Okay, so because we are calculating the power, so we have terminated with the detector mount and we are taking the output. So first of all, what we are doing, we can put the stub in such a way, the probe is inserted in such a way to the in a depth to get the minimum value. So as this graph you can see here, for this voltage versus distance graph, that means for slotted section we have pushed first we have calibrated the CRO test bench, then we are getting the first minimum value. This one we will get, so let's say this point reference value we are collecting, we are noted here. This is a simple reference value. Now without any difficulty we have now just get this minimum value. After that we are moving the point in one direction in such a way it will get the twice the minimum power value. Okay, just one end we are moving it like in a way, so just it will get the twice of the minimum value one end. So we now in this way, let's say we have moving the slotted section in such a way, we will get the twice of minimum value. This one. Okay. Generally, this will having the P minimum. The value of this P minimum is, if we will relate, that is the V minimum square. Okay. After that, we are just moving in a point which is twice of this minimum power. So in one direction, that means 2 P min proportional to Vx square, let's say, because this graph between the voltage and the distance. So we are now just calculate this value, and after taking the ratio of these two 1 by 2, 1 by 2 simply is equals to V minimum square by Vx square, or Vx value is equals to under root of 2 V min. So this we will get. So that means this point which we are having with us, that is the Px is equals to under root of 2 V minimum point, where we will get the point, we will note this point, and the distance point corresponding to this twice of minimum is, let's say, D1. We are now noting down it. After that, we will now take it into this reference position again. After that, we are moving to the twice minimum in the other direction. Okay, in the reverse direction, or we can say that. So at this point means the reading of voltage will be reached to this one under root of 2 V minimum, or 2 twice of power minimum. So we are getting this point, and this value, let's say, we will note it down, that is the D2. So this, what we will got, 2 minimum points we will get, this D1 and this. So this is the 2 minimum power point, 2 half power points we can get here. Okay, 2 half point of minimum we can now get. So we have noted down the D1 and the D2 in this way. So when we will get all these 2 points, so after that, now we have the relation of VSWR is equals to lambda G upon pi of D2 minus D1. This relation now we have with us. So after putting these 2 values in this equation, D2 and D1, we can get the value of VSWR. But here another unknown, that is the lambda G, that is the guide wavelength. So this guide wavelength now we can measure with the help of relation lambda G is equals to lambda naught upon under root of 1 minus lambda naught by lambda C square. Okay. By this relation, we can calculate the value of lambda G, that is the lambda naught upon under root of 1 minus lambda naught by lambda C square. So here the lambda naught, lambda C is the cutoff wavelength here, that is the simple cutoff wavelength with us. Now after that, this is lambda C, that is the cutoff wavelength, and its value for the TE10 mode, that is lambda C is equals to twice of A. Lambda C is equals to 2 into A. A is the broader dimension of the waveguide which we are going to use here. So in this way, we can now calculate the value of this lambda C, and the test bench which we are using for this test bench, the value of this A is also defined already. So we can calculate the value lambda C and this free space wavelength lambda naught. So with the help of these 2 values, we can calculate the value of lambda G and put the value of lambda G into this relation lambda G upon pi D2 minus D1. So with this help, now we can calculate the value of VSWR, where this D1 and D2 are the two minimum points. So it is also this, because of this method for the high VSWR will named as a double minima method. Here now, so this is for the measurement of VSWR. Now what we are doing here, next one, the same thing which I have already explained previously in this. So you can now in the bigger diagram you can look to this figure. Okay, the same thing which I discussed, also mentioned here, same. So we can now skip this one, no need to discuss for this. Now the next one topic for the present explanation, the measurement of attenuation. So attenuation is what? So this the attenuation, another property of any device to get attenuation. So how we can measure it through the micro test bench. So attenuation is the ratio of input power to the output power, and it is simply expressed in the terms of dB. So this is the relation of any measurement of attenuation, which is attenuation dB is equals to 10 log P in over P out. Okay, so where this P in is input power, P out is the output power. So in this, if we have the two values of this input power and the output power, ratio of these two will give the value of this attenuation. So in practice, we are providing some attenuation by the microwave component. So how this amount of attenuation can be measured, we can calculate with the help of two ways. First one, that is the power ratio method. Second one is the RF substitution method. RF substitution method. So with this help, now we can calculate here. So one by one we will discuss. So first one, that is the power ratio method. So in this method, you can see that the two arrangements are now setup 1 and setup 2. You can look here, this one. So in this first one, that is the microwave source, attenuator, frequency meter, slotted section, termination, and from slotted section we have the crystal detector, thermistor mount, and the power meter for just to measure the power. And for second setup, we are inserting the device whose attenuation is to be measured between the frequency meter and the slotted section. Here we are connecting this device whose attenuation has to be measured. This is the difference between these two setup. So in this, what we are doing, so in the setup 1, the input and output power of whole microwave test bench is done with the help of done without the device whose attenuation has to be calculated. Let some value we will now get here. Let's say P1. After that, the input, and what we are doing here now, we are just inserting one another device in the setup 2 whose attenuation has to be measured, this one, between this frequency meter and the slotted section. So again, what we are doing, we are just now input and output power of the whole microwave test bench is done with the device whose attenuation has to be calculated. Let's say some power now come here. Let's say its value is P2. So the ratio of these power when compared give the P1 by P2. We will compare two values we will get here. So now when we will compare both these two, so we can get the attenuated power or the attenuation amount in this. So in this way, we are just simply getting the ratio of power here. Okay. So this is one of the method. After that, what we are doing here, when we are moving, we are now just use the crystal detector here. So the drawback of this method is the power and the attenuation measure may not be accurate when the input power is low and attenuation of the network is large, just because of the crystal detector we are using, and it will having the some square law non-linear characteristics. So that's why it will not give the accurate amount of power in this. So what we are doing, so just to get the accuracy, we are calculating the attenuation with the another method, that is the RF substitution method. Okay, so in this method what we are doing, so first of all we have the two setup here, setup 1 and setup 2 with us. So in this microwave source is here, then attenuator, frequency meter, network whose attenuation is to be measured, slotted section, termination, then crystal thermistor mount, power meter. Means the simple this one same we are now using here. As the previous one setup 2, it is setup 1 for this one. So after that, now what we are doing in the setup 2 and in the RF substitution method, this network whose attenuation is to be measured is now changed or replaced with the variable precision attenuator. Thus one change in this setup of these two, that is the whose attenuation is to be measured, is replaced with this variable precision meter. Now the first one step, the output of the whole microwave test will be measured with the network whose attenuation has to be calculated. So that means some attenuated value input power what we are applying. So attenuator we are applying, so we will get ratio by ratio we can get the attenuation. Now from the setup 1. Now the output again from setup 2 we will calculate the power. The output power of the microwave test bench is measured by replacing the network with a precision calibrated attenuator by this one. So when we will calibrate this, now some value we will get. Now what we are doing, let's say its value will be P1, attenuated value, we have some values here, then some value we will get here. But what we are doing in this, the first one we are just simply, what actually we will do in this, we will attenuator have this one is the variable attenuator. So we can now by changing its knob, by doing some correction with the knob, we can get the another value. So we can now adjust this value in such a way so that we can get the same power of this one, because attenuation has to be calculated for this device, not for this one, but this device. So we will get this value. So same setup, when we are having this variable precision attenuator, we are doing adjusting the power in such a way so that we can get this value P1 same. So after getting this same value, we can get the how much correction we will done in the attenuator, variable attenuator. So it will give the exact value of this of attenuation. So in this way, we can now calculate the value of this attenuation. So in this way, now with the help of these two, so just what actually we are just adjustment here in this, with the help of adjustment we are calculating the attenuation value. So in this way we can get the exact value of the attenuation which we cannot get in the power ratio method. So with the help of these two methods, which one? This is power ratio and the RF substitution method, we can get the value of this attenuation. For dV we are calculating, so its value will be 10 log of P in over P out. So this is from my side for the measurement of these two characteristics of, or the two parameters of the microwave, and for any system, that is the VSWR and the attenuation through the microwave test bench. So thank you and Jai Hind.